Hello, my name is Andrea Gearhart, and I am proud to call myself a chemistry teacher. I have almost 25 years of classroom experience. I've taught all levels of chemistry in my early years of physical science and then applied, academic, honors, and advanced placement chemistry. I'm looking for a new role. I'm looking to apply my experience and my passion for the subject and for the process of learning to really be able to make a meaningful impact to help students really become deep thinkers and strong problem solvers. As was asked, I would like to share with you some specific examples of curricular writing. In 2018, I helped to co-write an honors chemistry curriculum. In 2018, we rewrote our core sciences. At Peters Township, I have written curriculum for physical science, applied, academic, honors, and advanced placement chemistry. We utilized in 2018 a platform called On Hand Schools, and we were asked to fulfill the requirements in that platform. And so for honors chemistry, a course description, the course materials, pacing guide, we divided our course into separate units. And then most importantly, we looked at the Pennsylvania Science and Technology Standards and knowing what would be encountered within this unit, developed essential questions, which the student themselves should be able to answer, ideally take that content and really be able to know it so well they can teach it to someone else. As I'm scanning down, you'll see the correlation with the state science and technology standards. I also want to show that, within our curriculum, we definitely developed differentiated instruction for students of varying academic levels, to be able to measure their understanding. I would like to share now the example of, in 2013, the curricula I wrote for AP Chemistry. In 2012, the College Board adjusted the curriculum of AP Chemistry. And here is my document that shows how what I teach at Peters Township meets the big ideas, the science practices, the learning objectives, and the enduring understanding set by the College Board. And so here is an outline of the labs that I do with my students or have them do. And then again, the science practices, the learning objectives, the enduring understandings, divided up into 9 weeks. Here is a breakdown of the different big ideas, essential understanding, learning objectives achieved in all of the chapters that I do, which the College Board calls it units, but that's how I divide it down per my textbook. I would like to share a specific example of a lesson. Lesson plans are always definitely more developed and detailed. And so to introduce electrochemistry, this is an example of what I commonly do with the AP students. They'll begin at their lab stations with their lab team members observing and operating the galvanic cell, really focusing on the parts. What parts are there? Very few students know the inner workings of a battery or why those parts are there. So instead of telling them, I want them to observe and then try to connect those observations with predicting how does it work? How is that voltmeter measuring a voltage? And then I'll be able to tell, do we need to talk about what voltage is and that kind of thing. So this is a great feeler exercise for me as well. What I do is use their observations. So they'll either, depending upon time, how quick my students work, put them on a big whiteboard or put them on note cards, also class size. How can I assess where they are and then know what we need so that by the end of the lesson that day, they will understand why everything has the parts that it does, how those parts work together to get electrical work out of a chemical reaction. I have mirrored the state standards that in science and technology that this lesson directly supports, and the College Board big idea or science practices and learning objectives and essential understandings. So it starts with their observations and then builds on theirs, correcting, enhancing, redirecting if needed. They've seen redox reactions before, and so it's making that connection. By the end, can they use correct terminology to label just a schematic? So if they know the reaction, can they identify the anode, the cathode? Do they understand the operation of a salt bridge? So from initial observations, do they now have an understanding of what those parts do? And we'll keep building on this as the unit goes. I also wanted to give an example of some assessment questions that I ask. So definitely accommodating the different levels of Bloom's taxonomy as well as levels of knowledge. In first year chem, it's a fine line between really getting them confident with this new course called chemistry, but having them deeply think and connect big concepts together. And so usually an assessment will start with some level 1 basic recall. But I like in this second example, to not just ask which of the following is a physical property, but just if the terminology is changed up a little bit, how can a physical property be measured? That, I think, sets some more real life scenarios for them and a little bit of deeper thought. I'm a firm believer in being able to really imagine and communicate things on the particulate level. So I think that also helps to just deepen that understanding, but also could they be given a particulate diagram of a before and an after, and then match that to a reaction, or in this case, if it's a physical or chemical change. For short answer questions, my students know it is quality, not necessarily quantity. And so can they, in a concrete and purposeful way, justify, explain, prove? So here's some examples that will get students to that deeper level of thinking. In AP, it's not just simple surface recall, but maybe recalling two things that match or connect. And so, for example, in this first question, not just what is the hybridization of carbon in CH4, but what is the hybridization and the bond angle? So, making multiple connections together. If they are given a claim, can they justify? Can they, provide the evidence that backs up the claim? And then how does that evidence connect with the claim? And I love to give them a student conclusion and then ask if that student was correct or not correct. So do they agree with the student's conclusion, and provide the evidence and the justification? I love questions that at first may seem, just a list, but this last example question really ties in their understanding of experimental design with the problem solving that achieves the objective of finding experimentally the enthalpy of reaction between a certain mass of magnesium and volume of solution. So they need to really think through what actions, what measurements will I collect? Measurements to ultimately do the calculation. They'll need the entire mass of the reactants. And so if they're given density, they'll need to calculate the mass of the solution, but measure the volume. Or will they have to measure the mass, measure the volume, and then get the mass of that? And then add to that the mass of the magnesium. Students often stumble a little bit with, they'll need the change in temperature for the calculation, but you can't measure change in temperature, you measure initial and final. So these are the kind of scenarios that really get them thinking in a deep way and connecting experimental hands-on experiences with, paper problems and bring it more to life. I very much look forward to speaking with someone further about this exceptional opportunity to work with Instructure. I myself, in the last 2 years, have developed 2 courses since our school district has adopted Canvas as our learning management system. And so I just applaud you for the creation of such an effective way to communicate and host and inspire learning for our children. I look forward to finding out more, and thank you for your time.